All right. So today I will be talking about my master's thesis, which is extending model checking using inductive proofs in distributed digital currency protocols. So I want to break down a little bit what I mean by that. So two tools that are really commonly used in formal verification are model checkers and theorem provers. Model checkers are really effective at verifying distributed systems because they include constructs for message passing and asynchronous processes. It makes it really easy to directly model distributed protocols. Model checkers will exhaustively search the behavior of a system to automatically prove both safety and liveness properties. Safety properties are properties that have a single state counterexample. For instance, you're never driving while unbuckled is a safety property, and liveness properties are properties that have an infinite counterexample. For instance, if you continue driving, you eventually reach your destination. So model checkers are really effective at verifying these types of properties, but it's computationally complex. Exhaustively searching the behavior of the system grows exponentially as you add more entities into the system. So it's only really suitable for small systems. On the other hand, we have theorem provers, which allow for machine-checked proofs. And that allows us to use very powerful reasoning techniques, including induction, which allows us to prove properties of arbitrarily large or even infinite systems. However, directly implementing distributed protocols often leads to a very complicated proof. And each property you'd like to prove has to be individually proven, which is non-trivial, and liveness properties are especially difficult to prove. So you can see that the pros and cons here overlap, which kind of leads to my thesis, which is that combining model checkers and theorem provers can be an effective method to verify distributed algorithms that support any number of participants. So the way that we're going to go about showing this is using a case study, and we're going to be using MyCHIPs, which is a digital currency that Kyle Bateman proposed. It's a novel digital currency based on personal credit, and we picked it as a case study because one, Kyle was very interested in having it done, and two, it has properties that we'd like to verify on a non-trivial distributed algorithm. So to understand my work, it's good to get a little bit of an understanding of what MyCHIPs is. So the way to begin thinking about MyCHIPs is to consider a barter that involves more than two people. So for instance, Bob, his car broke down and he needs it fixed, and Cindy is able to fix his car. But Cindy would really like a well dug on her property, which John is willing to do. But John would really like solar panels installed on his roof, which happens to be what Bob is good at. So you can see that if everyone got together and did what they were good at, everyone would be happy. So how can we facilitate this exchange? Well, using US dollars, Bob, he's just up a tree. He really needs his car fixed, so he's going to go to the bank. He'll take that cash and give it to Cindy, who will fix the car. Cindy will take that same cash, give it to John to dig the well, and John will take that same cash and give it back to Bob to install the solar panels. Then Bob brings it back to the bank. The bank says, great, but you owe us a little bit of interest. So the question is, can we facilitate this exchange without the need for the bank? And the way that MyCHIPs goes about doing this is using personal credit, IOUs, right? So Bob will give Cindy an IOU, Cindy will give John an IOU, and John will give Bob an IOU. And in that way, they create this cycle of debt. They all owe each other. And what MyCHIPs will do is identify that cycle of debt and arrange for them all to forgive each other. So you might imagine that Bob could say to John, hey, if you can get Cindy to forgive my debt, I'll forgive your debt. And MyCHIPs is a digital system that arranges for that type of forgiveness. And the way it does that is using a distributed algorithm called a credit lift. So I'm going to give one example of what could happen during a credit lift that shows some of the features of it, but we'll formally define what the credit lift does using mealy machines later. So the credit lift consists of three phases: the discovery phase, which is not shown here, the promise phase, and the commit phase. In the discovery phase, we identify those cycles of debt, but this phase, there's no value that is exchanged, so it's not as critical to verify the properties during that stage. So we're focusing, and this work analyzes the promise phase and the commit phase to ensure that the properties hold. In the credit lift, there are three unique types of actors. There's an originator, which is someone that's in the cycle of debt that initiates the lift process. You have any number of relay nodes, which is just some participant that's in the cycle of debt that would like to participate in the lift. And then there's a third type, that's referee, which serves as a consensus object to ensure that if stuff goes wrong, we can correctly decide whether we're going to continue with the lift or whether we're going to roll back. And its role is going to be more clear through this example. So to start, the originator is going to send a promise to relay 1. This promise is essentially saying, if this promise goes all the way around and everyone agrees, I promise to forgive your debt, right? And in this promise, there are 3 pieces of critical data. There is the amount that's being forgiven. There is a timestamp, which is some future point in time that we say, if we haven't all agreed by this point, we're going to roll back and cancel this lift. And then there's a referee. And the referee is going to serve as the authoritative clock for deciding whether that timestamp has expired or not. It's also going to serve as a node that you can reach out to if you have questions about the status of the lift. So when the originator sends the promise to relay 1, if relay 1 still wants to participate and agrees to the terms, it will forward and send its own promise to relay 2, which will in turn forward to its successor, which in this example happens to be the originator. So once that promise has gone all the way around the cycle, the originator receives it and knows that everyone has agreed and is going to reach out to the referee saying, hey, everyone's agreed, can we commit this lift? Send a message to the referee. The referee will look at the lift, look at the timestamp and compare it to its own clock and say, if it's past the time, we'll say, oh, no, we're going to nullify this. If it's within time, then it will send a signature. So in this case, it's within time and the referee sends a signature. From there, the originator wants to claim its forgiveness from relay 2. So it forwards that signature to relay 2. And when relay 2 receives it, unfortunately, some error occurs and relay 2 crashes. Because of that, relay 2 fails to forward the signature. Hey, Bryson. Yeah, so relay 1 never receives this signature. So it's left in an uncompleted state, and it, according to its own clock, it thinks it should have been finished by now. It's past the timestamp. So what relay 1's going to do is reach out to the referee and say, hey, what is the status of this lift? And the referee will look at its records, say, oh, yes, I remember this lift. I provided a signature before, and it's going to reply with a signature for relay 1. And this way, despite the failure in relay 2, relay 1 is able to know that the lift is committed. And you can see from this that we achieve consensus between the active nodes here, despite failures occurring. So that's kind of an example that gets you a feel for how this algorithm works, but how we define the behavior of each of these types of entities is with these mealy machines. Now, don't want to go into too much detail here, but suffice it to say that this is the behavior that is expected from each of these, and this is how we'll model the behavior. So there are 4 properties that we'd like to verify on the MyCHIP system. One is termination. It's not acceptable for a lift to remain in an uncompleted state forever. So we're going to claim that it always eventually will be committed or nullified. Everyone will eventually decide what to do. And the second, consensus. If everyone agrees to commit, or if any node thinks that we're going to commit, every node should agree to commit. We have consensus on whether we commit or roll back. The third property is harmless, which in a typical lift, if everything goes well, the change in balance for a node should be 0. You get forgiven as much as you forgive. However, if things go wrong, we want to allow for the possibility that you're better off. So we say that the balance is greater or equal. And the last thing is agreement. If you have 2 nodes that have a change in balance between them, they agree on that change in balance. Those are the 4 properties we'd like to verify. And we'd like to verify it on an arbitrarily large system, a system with any number of nodes in this ring, right? And you can see in this model, we have this ... here, which represents an arbitrary number of relay nodes. And really, that's the hard part. And of course, I'm not the only person to think about, and I'm not the first person to think about this kind of problem. So there's 2 pieces of related work that I want to highlight in order to frame my work. So the first piece of related work is infinite state model checking, which has its roots in a paper by Clark, Grunberg, and Brown in 1986. And what they were considering is if we have a system that is made out of any number of identical processes, can we look at just 2 of those processes, do a careful analysis of that, and show that properties of the 2 extend, such as deadlock freedom and such, extend to a larger system? And the way that they go about doing that is working directly on the state of the system. So you might imagine that a system starts in its initial state, and using our example for MyCHIPs, we might transition to state one when the originator sends its first promise, then some processing happens, we go to state two, then the first relay sends its promise, we go to state three, and then from there, there's this repetition where we go from one relay node to the next, and there's this repetition of behavior. These states are technically unique, but what Clark, Grunberg, and Brown did was saying, if we can consider these the same and state match those, we can have a sound approximation. So what they're going to do is show that two nodes, if considered equivalent, is a sound approximation. If there is no error found in this, it's an over-approximation, then there can be no error in the real system. And work continued on this, and we're effectively adjusting the state matching to weaken that state matching or abstract that state matching. In this way, it's kind of akin to abstract interpretation. So the second piece of related work I want to talk about is trace theory, which is something that was created by Dill in 1988 as part of his master's thesis. And Dill was working in an entirely different context. He wanted to do hierarchical verification of electronic circuits. The way that he went about doing that is using what is now known as trace theory. So what he considered is, if we look at the inputs and outputs of this electronic module, we can create a trace of events. So for instance, this module, we might see a transition happen on A. Then as that's processing, very quickly a transition happens on C. And C's circuitry is actually faster. So then we see a transition on F, followed by a transition on E. This is a possible trace of events for this module. However, if we have a transition on A immediately followed by a transition on F, there's no real causal reason for this to happen in this module. So this is not a valid trace of this module. So what Dill considered is, if we just consider each module as a black box and look only at the trace of events, can we determine if one module is a safe substitution for another? And Dill defines a relation called conformance, which if one set of traces conforms to another set of traces, then that means one module is a safe substitution for another module. So that's the second piece of related work. So our approach, you can think of as solving a very similar problem as Clark, Grunberg, and Brown, but we're going to use the tools of trace theory in order to solve it. So the way you can go about thinking about that is, in a MyCHIP system, there's always exactly one originator, exactly one referee, and there's any number of relay nodes. So what we're going to do is take this relay node and replace it with a black box. And we'll consider what could be in this black box. Now, of course, if we just have a relay node in the black box, we expect the behavior of the system to be the same. Everything's going to work exactly the same. The question is, can we put a chain of n relay nodes in this black box and have this conform, trace theory conform, the inputs and outputs are equivalent so that the rest of the system is just unaware of what's in the box, not being a single relay node. Now, in practice, it's pretty difficult to prove this directly with the non-deterministic choices of mealy machines. It's a pretty difficult proof. We have a trick up our sleeve. Rather than defining these empirically, instead, we're going to define a series of validity rules. And these validity rules are going to define the possible inputs and outputs, the traces of this module. In this way, it's kind of akin to the Chinese room argument, where we have inputs and there's a series of rules we follow to generate the outputs, right? So as it turns out, defining it this way makes it much simpler to prove that a chain of n of these validity rules concatenated together conforms to n minus 1. Conforms to 1. So here's kind of the game plan of how we're going to prove it. We're going to use an inductive proof that has a base case that we're going to prove with model checking. That base case is just a system with a single referee, a single originator, and a single relay node. We're going to verify that all four properties hold there. Then we're going to perform an inductive step using two lemmas to help us. One is conformance of a chain of n plus 1 relay nodes to a chain of n relay nodes using that black box validity rules model. That's the B here, black box. Then the second piece is we're going to use conformance to show equivalence between the black box validity rules and a single relay node. And using that, we can prove an inductive step. So to give the intuition of that inductive proof, we're going to start with the base system. We'll verify that all the properties hold on this base system with originator, referee, and a relay node. Then using our third lemma, conformance equivalence, we can convert this relay node into the validity rules definition. Then using our second lemma, we can show that a chain of n+1 to, in this case, a chain of n+1 relay nodes, part of the black box definition, conform to that, which means that none of the properties have been changed here. Then finally, we use our third lemma again to convert those black box models back into the definition. And from there, that's our inductive step that a chain of n+1 relay nodes conforms to n relay nodes, and the properties continue to hold for an arbitrarily large system. So that's the proof, but we have three lemmas we'd like to prove, and I'm going to walk through each of them, starting with the base case. So like I said, the base case we're going to prove using model checking. And model checking is very good at directly implementing distributed protocols. However, we want to make sure that this protocol is as simple as possible. Because of that step 3, the conformance equivalence, we have to write validity rules that exactly match this behavior. So we want to make sure it's as simple as possible to make writing those validity rules as simple as possible. So one thing to note is in our model checking analysis, we don't directly model time. Rather, instead, we have each node that would make a decision based on time, make that a non-deterministic decision. They try both ways and we'll see what happens, right? So because of that, anything that can be considered just a delay can be ignored. It's not going to change our analysis. So we're going to search here looking for a delay. So there's one case that we can point out that is really just a delay, and that's the case where this relay node, it's received a promise, and it's going to request the status from the referee. When the referee receives that status, it's going to look at its timestamp and say, well, the time hasn't expired yet, so it's not void, but the originator hasn't committed yet, so it's not good either. So it's going to respond penned. And you'll note that there's a self-transition from the relay node to the same state and from the referee to the same state. So no, the state doesn't change after this. So it's really equivalent to a delay. We also can note that the originator has the same problem. So in order to fix this delay, we can just remove this edge here, whereas a referee responds penned. Now I want to be really careful here, make sure we're not changing anything. So I actually implemented both. And the 4 properties we care about hold in both of these systems, but we're going to use this as our base case for our inductive proof. So this is the state, which I described in more detail in the thesis, but I just want to highlight one piece here that can be a little bit confusing. So the second property here, which is consensus, you'll see that we use a by implication, which effectively what we're saying is if any of them believe that we're in the good state we've committed, then all of them should believe we're in the good state we're committed. Now you might be tempted to say, well, why don't we just say that the states are equal? And there's one case that makes that not true that we'd like to allow. And that case is if the originator were to start sending a promise, but it fails to arrive, then none of the other relay nodes in the system are even aware that the lift exists. They're all in the no lift state, right? Eventually, the originator will time out, reach out to the referee, say, hey, this is not completed in time, right? The referee will go into the void state. The originator will go into the void state, but all the rest of the nodes in the system will be left in the no lift state. And that's okay because we didn't commit, nobody committed, and we're going to allow that. So that's why we defined it this way. So our model checking results, we used a tool called Spin to do our model checking. And when we evaluated those 4 properties, it evaluated over 15,000 states and 172,000 edges between those states and found no violations of the properties. On my machine, it took a little under 10.5 seconds to do this analysis. So with that, we have proven the base case that the properties hold on the original small system. Next, we're going to move on to the conformance of a chain of n+1 relay nodes to n relay nodes in the black box model. And to do that, we'll want to formally define conformance. So Dill in his work provides a sufficient rule that shows conformance. Conformance is pretty tricky to strictly lock down because it's really equivalent to safe substitution. And there's lots of cases where one module might be a safe substitution for another. And it's difficult to find that exactly, but you can create a rule that if this rule holds, that implies safe substitution. There might be cases where it doesn't hold and it's safe to substitute, but this ensures that it will. So this is based on Dill's work. And this left-hand side implies the conformance, right? And I want to break down the pieces here. There's a lot to it. So we'll start with projection. So the idea of projection is that if we have a replacement module and an original module, the alphabet of possible events between those might not be the same. So really the goal of projection is just to make sure that we match alphabets. So for example, in our MyCHIP system, we might have the node with ID 0, send a promise, promise send, the node with ID 1, promise receive, so on and so forth, the node with ID 2, promise receive, node with ID 2, promise send. This is a trace of events for a system with 3 nodes in the chain of size 3. And we might like to project this onto a system of size 2. Now, if there's a system of size 2, there won't be a node with ID 2. So what we're effectively going to do is just omit those events from our trace. And that gives us a new projected trace, right? And you can think of this as if there's an output of a module that isn't part of the original, but is part of the replacement module, we just leave that output unconnected. Those events are ignored. Similarly with inputs, if there's an input to this module, we just say that that input never occurs and look at that. So that defines projection and what we mean by this. And then there is F, which is the failure set of the module R. Now, what the failure set is it's the set of traces that if we were to observe this trace of events on the module, we would expect an internal error to occur in the module. Now, Dill's assumption is that if a module experiences an internal error, it's not going to behave properly and it's going to cause the whole system to fail. However, in our case, we are actually interested in the case where nodes experience an internal error. And that's part of what we're hoping to prove that MyCHIPs is hardened against, right? So because of that, we're not going to consider any of that behavior as failures. We're just going to consider part of that the possible behavior of one of these modules. So because of that, we're going to define the failure set for all of our modules to be the empty set, which allows us to reduce this to this simpler version, right? So this last piece, this P is the possible set of traces for the module R. So that's all the possible combinations of inputs and outputs. And one thing that was confusing to me at first is this idea of a subset. If it's a subset, couldn't we have the empty set, right? In that case, couldn't we just have a block of wood in here? That's not always going to work, right? But that's not quite right. It's not a subset of the traces. It's a subset of the set of traces. So if a block of wood were to be a safe substitution, that would imply that one of the possible behaviors of our original system is to do nothing in response to input. So what does this subset do for us? If for a given input, there are 2 possible outputs that could occur in the original system, it is acceptable for the replacement to always choose one of those possible outputs. So that's kind of where that comes from. So with conformance formally defined here, we now have the tools to talk about a chain of n+1 relay nodes conforming to a chain of n relay nodes. And to do that, for our black box model, we're looking at a possible set of traces. We define the possible set. Using a series of validity rules. The validity rules define what is possible for the module, right? So there are 8 rules here. I don't want to get into too much detail here, but suffice it to say that we require that certain actions are present and we enforce a partial order of events on those actions. For you to point out, all receives causal ensures that we only receive a message after a message has been sent, as well as phase sequence correct, which ensures that we send promises first, commits later, that sort of thing. So with those validity rules, we'd like to prove this conformance property. So we have a series of lemmas that build up from basic principles up to this larger conforms to smaller proof, right? So we'd like to prove that a chain of n+1 relay nodes conforms to a chain of n relay nodes. Larger conforms to smaller. And each of these lemmas build up to prove that, and I want to highlight a couple of these. So has required actions independent of projection, as well as a few others. This is just saying that if the rule holds for a trace before we project, then it's going to hold after we project. It's independent of projection. And that's true for most of the rules, with one exception. All receives causal. is not independent of projection. You might imagine that the node with ID 0 receives a message from the node with ID n+1. And when we project to size n, that send for n+1 is now missing, which makes it look like this receive is no longer causal. However, we can prove that for all valid systems, for that, if there's that lost message from node n+1, there's an equivalent message from node n that was going to go to node n+1 that can be remapped to go to node with ID 0 and show that that receives causal holds for all valid systems. So that was really the core piece of the proof, the most difficult part of the proof. So with that kind of described, I want to formally define this larger conforms to smaller. So we say for all T set of traces, right, that is a ordered list of actions, right? If T is valid, this trace is valid for size n+1 and n is greater than 1, then that implies that when we project that trace to size n, that projected trace is valid for size n. So we want to show that this implies conformance. So this is what we need to prove to show conformance. And I give a formal proof in my thesis document, but just to give you a little bit of intuition and mapping here, we have T, all traces that are valid for size n+1, the possible traces of a system of size n+1 that maps here. And we're going to take that T and plug it in here and project it. We're going to project it to size n, and we're going to say that that's within the set of the possible traces for size n, meaning it's valid for size n. So you can kind of see how that maps. So given that, if we prove this, we've proven conformance. So with our theorem prover, there were 24 lemmas and theorems that we proved. The proof script spanned 1,960 lines of code, and all our lemmas and theorems proved out. On my machine, executing that verification step took a little under 8 seconds. So that proves our second lemma, the conformance of n+1 relay nodes to n relay nodes using our black box model. And last, we want to prove conformance equivalence between our definition, the mealy machines, and our validity rules black box model. So with this conformance, we can again use our sufficient proof for conformance. We break it into 2 pieces here. You'll notice that we project the black box model to the mealy machine as well as the mealy machine to the black box model. So that doesn't really help us much, and by design, the black box model and the mealy machines have the same alphabet of events anyway, so we can omit this projection part. So there's these 2 pieces here that we'd like to prove, and if you look at this carefully, you'll note that if we have one subset of the other and the other subset of the one, that just means they must be equivalent. However, it's easier to prove each of these individually, so we'll prove them one at a time, beginning with the one on the right. So we'd like to prove that all of the traces within our mealy machine model are within the possible traces of the black box model, or said differently, there doesn't exist a trace in the mealy machine model that is not within the black box model. Said differently again, there doesn't exist a trace in the mealy machine model that violates the validity rules, specifically for size 2, because our mealy machine model has the originator and 1 relay node, so it's size 2. So this is the exact type of problem that model checkers were built to solve. So what we can do is encode all of our validity rules as properties and exhaustively search to make sure that there isn't a trace that violates these properties. And when we do that, the model checker evaluates over 11,000 unique states, 73,000 edges between those states. And there's a lot of properties we had to check, so it took quite a little bit of time. It took just under 23.5 seconds on my machine. And we proved that the validity rules for size 2 were never violated in our mealy machine model. So that proves this right-hand side. And now we've got to do this left-hand side for conformance. So we'd like to say that all the traces within the black box model are considered in the mealy machine model, right? Now to do this, we can consider all the possible traces of the black box model, and the set of all possible traces is actually infinitely large, and individual traces within it can be infinitely long. You can send messages multiple times, you can reach out to the referee multiple times, but each of these messages and these events are designed to be idempotent. Once you've received, or once this message has occurred for the first time, it will change the state, but if the event occurs again, it's not going to change the state. And because of that, we can divide our set of traces into equivalence classes, with a canonical member being the member that has each type of event exactly once. So using our validity rules for certain actions being present and a partial order of events, we can define 9. There are 9 possible equivalence classes. So we might receive a promise, fail to send a promise, then we'll status send to the referee and receive that status from the referee. Or for instance, we might send a promise, we'll receive a promise, then we'll send a promise, we'll request the status from the referee, then we receive the commit from our neighbor, we send the commit to our neighbor, and then we finally receive the status from the referee. So there's all these possible combinations and we evaluate all of them, right? So the goal is if we can find each of these equivalence classes in our mealy machine model, in our model checker, then we can show this subset. So to do that, we can create automaton in our model checker that accepts these equivalence classes, and we're going to find a witness trace for each of them. So we evaluate relatively few states. On the smallest case, we had just 36 states evaluated before we found a witness trace. On the worst case, it was 8,300 states were evaluated before we found a witness trace, but we found all 9 witness traces. And there's a lot of traces to look for. On my machine, it took a little over 28 seconds to find all those traces. So because of that, we can believe that the black box model is a subset of the mealy machine. And that proves our last piece, our last lemma here. And now we've proven all 3 of our lemmas, which we used for that inductive proof to show that the properties we care about extend. So in conclusion, there are 4 contributions I want to highlight. The first is that we extended model checking results using an inductive proof. In doing that, we used conformance in 2 unique ways. We used conformance to move from one implementation, the black box model, to another, the mealy machine model. We swapped between those. We also used conformance as part of our inductive step. I want to point out that this black box approach, the inductive proof doesn't know anything about the properties we tried to verify. And because of that, if there's some other property we'd like to verify in the future, all we have to do is encode that in our model checker and verify that it holds, and we know that it will extend to an arbitrarily large system. Last, I just want to make sure this is super clear. We've proven that those 4 properties we care about hold on the MyCHIPs lift protocol with an arbitrary number of participating nodes. Thank you, that's it. And I look forward to your questions.
We welcome anyone to ask questions. It's an open forum here. The challenge and flummox Kyle as best we can.
Yeah. Don't get too flustered.
So the machine looked like it took like a minute and a half to solve everything. Why did it take so long?
Yeah, it's a good question, right? That's how it works with research, right? It takes a long time the first time, but the next time it might be a lot faster, right?
You mentioned that you spent a year with a little unsolved asterisk. Was it always the same asterisk, or did you solve one and did that lead to another one?
Yeah.
Explain that process.
So yeah, the process is we would prove it, and it's all proven with maybe we had to admit one little proof, right? One little thing that, oh yeah, that's trivial, we'll be able to solve that. And then we break that into like 4 or 5 pieces. We solve 3 of them. Okay, it's one little problem. So I know we break that into 4 or 5 pieces. We solve all but one of them. And eventually we got to the point where that last one proved out without having to break it into smaller, simpler problems. And it proved out.
So did you end up retaining each one of those steps, or were you able to go back to the beginning and reframe the problem in such a way that it was not such a rabbit hole? Were you able to sort of reparallelize the process from the beginning, or do you still follow that series of same steps?
Yeah, I think I have a mix where sometimes I had to rethink the problem again and redefine it, in which case a lot of the other stuff was lost. But sometimes it was, like I said, just breaking it into smaller problems and it's retained in the code. Maybe it would take a little bit of sleuthing to look through it and figure out how my process there, but it's there.
Which of those was the one that ate up most of your time? Was it the receives causal? That
Yeah.
was the whole
Yep.
issue.
That is the whole issue. All the others prove out fairly simply. It's just tricky because when you remove this action, right, it makes it appear that it's not causal. And there are a lot of cases, possible cases where these actions get projected out, and we had to look at each of them and show that, well, if it's valid, either this case isn't possible or there's some message that remaps now and works well. Yeah, and part of the core insight that made that possible is we defined in our projection a size. And defined for all receives causal, we said a send is equivalent, or a send matches up with that receive if the destination and the source are equal mod the size, which means if you tried to send to set n+1, but it's size n, that's equivalent to sending to 0. And that mathematical foundation allowed us to formally define that remapping we're talking about. And when we remove this node, then its new successor is now node 0. That's probably the trickiest part, is making that work. Yeah, totally.
So I may have misunderstood bits of this, but you said that you removed a self edge from the referee model.
Mhm.
And as I understood it, the inductive proof was based off of this slightly simpler
Mhm.
model. How does this prove the validity with the self edge?
Yeah, so that is a good question. We believe that they're equivalent, right? And the way that we're at least equivalent in terms of the properties we care about. And the way we proved that is we actually implemented both with the self edge and without the self edge. And we proved, in fact, it's in the repository, you can actually look at both. And we proved that the properties hold on both. So in that way, they're equivalent with the properties we care about.
And you believe the inductive proof, because that was all in spin, right?
Yeah, so that was all in spin, and the inductive proof is in Coq, right?
Mhm.
Yeah, so we believe that it continues to map. Yeah, either way, and the reason we believe that is, like I was talking about, it's equivalent to a delay. And in our analysis, delays, we don't directly model time, so it's a non-deterministic choice anyway. So a delay is not going to change the behavior of the system.
Because doesn't the spin model effectively model an unbounded delay or a bounded delay in any variation of delay in between?
Right, yeah, so it can't be infinitely long because we say always eventually, but it can be any finitely long, could be millions of years. That's one of the possibilities that we consider.
That's only if the original lift proposal proposed an expiration that long.
Yeah, so the idea is that a message from one peer to another might take a million years to finally arrive, but we do ensure that messages to and from the referee is always available, right? So I guess there is the case where a message from the referee does take a long time. That's something that's considered in the model. I think that's highly unlikely, right, in a real system. But there is the case where we're waiting for the referee. We know eventually they'll respond. So you're kind of left until the referee responds.
Is it true? Would you say it's true based on your analysis that if the referee fails, but every other node in the system succeeds, that you still are live? Or did you test that?
No, so in our analysis, one of the core things is that the referee cannot fail. Otherwise, it actually maps to the two generals problem. It's impossible to prove consensus. So we have to have at least one node that can never fail, and that's what the referee is meant to serve.
So if the referee goes unavailable, the transaction has to wait until the referee comes back online.
Yes, that's right.
And that's when you get resolution.
Yep.
That sounds right.
So make sure you trust the referee to be online and available and honest, right?
Yeah, because the referee is the only authoritative voice for deciding whether or not the commit has expired or.
And as an implementation detail, you might have the originator and the referee actually be on the same machine, the same node, right? But in our model, we'd like to keep, if you do that, make sure the states are separate, just to make sure that the model holds up, right?
If the loop succeeds though, and the originator is successfully able to reach the referee and everyone else, but nobody else can reach the referee, is it not true that that transaction could also succeed with surety?
Yeah, yes, that could totally work.
As long as the referee generates the signature
To the originator.
to the originator,
Doesn't have to talk to anyone.
doesn't have to talk to anyone else.
Yeah, and an ideal situation, the referee is reached out exactly once, right? from the originator on it.
I have a couple more questions.
Yeah, please, no, ask away. We want to see them flummoxed.
So based on your analysis. Would it be possible to take an actual reference implementation of a server that's attempted to implement this protocol and make that your black box? And could you use the same modeling techniques that you've used in order to submit that server to a number of tests that would determine whether it's compliant with the way you've modeled this problem? Could you test an actual implementation?
Yeah, so I'm imagining an actual implementation might have the same types of mealy machines, kind of the same core structure to it, but there's additional states and additional things for error handling and such. And we'd like to show that they're kind of equivalent, that somebody interacting with the actual implementation and someone interacting with this idealized model won't know the difference. So we can use that conformance equivalence idea for that as well. So we can model both of them and look at that way.
Spin or cock, give us any data set or any tools or anything to do that? Or would a person be starting from scratch to try to do a real live validation like this?
Yeah, so that's a good question. Your goal is to be able to verify your real implementation, right?
To bring it back to the way you've modeled this question and say, does the real implementation behave as the way you modeled it?
Yeah, I think that process would be largely manual. You're trying to make sure that it matches up with the model. And that might be an interesting area of research, is can we automatically generate tests that make sure that we're matching what the model says and that sort of thing. So that might be something to look at in the future as well.
Do you think the number of tests would be identical to the number of states or traces that you generated in this, or would it be some totally different problem?
Yeah, that's a good question. I mean, ideally, you wouldn't want to have the 15,000 tests, right? That would take a really long time to walk through, right?
That would be exhaustive, though.
It sure would, yeah. That might be possible to get spin to emit something. Basically, what we're trying to do is it emits a current state of the system, and we'd like to create a test that causes the implementation to be in that current state.
Experience that.
And that is kind of tricky because tests are usually you give it an input and execute it. You don't usually give it a state that it's searching for. So that might be an interesting problem to try and solve, is can you generate tests that evoke this state?
And somebody else have a.
Yeah, you asked a question about like what kind of tools do Spin or Cock provide to do this. The use of Spin does complicate it, but with Cock you could implement an actual system and prove within Cock that it is consistent with this model. And then you could use a feature of Cock called extraction, which would essentially compile it to, some actual programming language that you could run. You could run your artifacts and you would know it was consistent with this model.
Are you saying that it would produce the server for you? Or are you saying it would produce the test routine?
It would produce the server.
You'd implement it in Cock's language, which is a non-trivial exercise, but yeah, that would.
It's been done.
Yeah, so people have done compilers, anything that's really safety critical.
Jay McCarthy proved our reentrancy on a common server using Cock and deployed it. But it'd be more, I think you'd have more success showing a conformance relation between an implementation of an entity in the protocol and the mealy machine. And it'd probably be easier to go out because you already know anything that implements the mealy machine satisfies the properties. So now you have a hierarchical system where you just have to show each entity correctly implements that mealy machine.
Is that just a series of state transitions? Or
You could probably do it with just a declarative contract that reasons over the input space and says what could be on the output.
And I just got some clarity on that idea. If you have an implementation for your server that's different, you can create a model and Spin that's more accurate to that implementation and use that same conformance equivalence where we prove that all the validity rules hold and we prove that each of these equivalence classes are within that. We can use that to prove a conformance equivalence. So we're not saying that it's equivalent to our original model, but we're saying that the properties of this model continue to extend for a large model. So we can verify those properties on that.
Yeah. Might actually be able to show that, yeah, you could do it either way, but I think you'd attack it one entity at a time. So you could show a property of a relay, show a property of the server, and show a property of the referee. And then conclude the overall system properties. But anytime you go to try and prove something in actual implementation, it gets really, it'd take more than the year to go after those, because there's just a
Year of analysis or of CPU time.
of analysis, and it'd be very specialized and heavily manual. It just, there's so many steps as you move from a high level language down to an actual deployed implementation. And there's a lot of assumptions made along the way. So to really button it up tight, it's a big lift.
There's two paths there, like Kimball was saying. There's, you can go through, try and create tests and give yourself high assurance that it's going to match, or you can go through and implement it in Coq and have a proven case that matches, and then extract that using proven compilers that work on.
Is Cox ML, is that verified?
It wasn't as of a decade ago, but that may have been patched up, and there are other ways you could do to other things. You
Submit to KML, because KML is verified now.
That's what I was gonna say.
So they have a K.
Maybe, I don't know if they do, but I wouldn't be surprised.
So there's very few compiler chains verified all the way down to the binary to preserve the original meaning of the high level language, and KML is one of those compiler chains, but it's not entirely efficient in its generated code. It's quite the opposite.
It's correct.
But it's correct.
Do we want it verified or do we want it fast, right?
Good questions. Okay, any other questions? Okay.
Well, now we get the hard questions, right? The ones you're afraid to ask in front of other people.
Yeah, so at this point, we have a transition where the public audience is typically excused while the committee asks questions of Kyle in private. Would the committee would you like to ask some questions of Kyle?
We'll load the questions in.
Okay, fantastic. So we'll thank Kyle again. Like our general audience and.
Oh, Doom, right? Yeah.
Good job, Kyle. I don't know.